320 million miles from Earth, a spacecraft is about to attempt the impossible. Rosetta is going to catch a comet and send a lander onto its surface.
We're attempting something unparalleled in spaceflight.
It's got to be one of the most challenging missions I've ever been privileged to be involved with.
The comet is traveling at 41,000 miles per hour. Every second, tons of gas, ice, and dust erupt from its surface. Landing on this monster is a colossal undertaking.
We're going to scratch and sniff the surface to get a real idea of what the comet is made of.
If successful, this mission can answer one of mankind's biggest questions: how life began on Earth.
By unlocking comets, we can really hope to unlock the whole story of the origin of the building blocks of life.
January the 20th, 2014. As the sun rises over California, NASA's giant 230-foot deep space tracking station, Goldstone, turns skyward. Half a world away in Australia, the Canberra telescope rotates to the same point in the sky. These two Goliaths are among the most sensitive telecommunications antenna ever built. Today, they're part of a massive international effort to make contact with a spacecraft called Rosetta.
5, 4, 3, 2, unité, top, allumage moteur vulcain.
Rosetta was launched over 10 years ago. Its mission to chase down and plant a lander on a comet. In order to save power, she was put into hibernation nearly 3 years ago. No one has heard from her since. The telescope's data is streamed live to the European Space Agency's mission control in Darmstadt, Germany. The world's press has gathered here because at 10 a.m., Rosetta should wake up and begin the final phase of its daring mission. 30 years of planning, $1.7 billion of investment, and the reputation of some of the world's most influential scientists and engineers hang in the balance.
We've never done this before.
Professor Mark McCaughrean is one of the European Space Agency's most senior scientific figures and champion of their high-cost, high-risk mission to an alien world.
If Rosetta doesn't wake up, we just don't have a mission. We can as well go home and just start working on something else. If it doesn't wake up today, we don't have anything.
Dr. Matt Taylor, project scientist. He is in charge of the scientific instruments on board Rosetta.
It is a really big day today. I'm feeling apprehensive, but also pretty confident that we're going to get Rosetta back after 31 months of hibernation. It was designed to do this, but there's always a little bit of apprehension when you're waiting.
Andrea Acomazzo heads up Rosetta's flight team. He is ultimately responsible for getting Rosetta to the comet safely.
We're convinced we have done all what we could to design the spacecraft to survive. We're also convinced the spacecraft can make it. But technically speaking, there are many things that can go wrong.
Rosetta's last signal, received back in June 2011, placed her 341 million miles from Earth. Using the data, Andrea and his team predict that Rosetta will have traveled another 450 million miles to an area near Jupiter's orbit. This is where NASA's telescopes now point. But all they pick up are the background radio signals from that part of the sky. Rosetta has been programmed to fire a radio pulse back to Earth to verify that it is awake. Its signal should create a spike above the background noise. Finding Rosetta is a massive challenge. The spacecraft is but a tiny speck in infinite space. Its core no bigger than a family SUV, its solar panels shorter than the length of 2 articulated lorries. But inside this tightly packed bundle is a marvel of engineering. An automated laboratory full of scientific equipment and cameras. And at its center, a lander the size of a washing machine, called Philae. Rosetta is going to try and plant Philae on one of the most enigmatic objects in space. Comets are primordial, city-sized boulders of ice and dust that roam the outer solar system, beyond the planets. But sometimes one of these distant comets gets knocked off course and comes much closer to Earth. As they do so, they put on an incredible display. These are the comets we see in the night sky. Rosetta will follow one of these icy travelers as it becomes active on its journey round the sun.
To get next to a comet and accompany this comet as it barrels into the inner solar system, that's difficult. So that's a first.
This is the first time we have ever deployed a lander on a comet. We're going to scratch and sniff the surface to get a real idea of what the comet is made of.
Rosetta has got to be a 10 out of 10 in terms of the challenges that we face among the missions I've ever been involved in.
Rosetta presents a once-in-a-lifetime opportunity to answer some fundamental questions. What are comets made of? What can they tell us about how our solar system evolved? And most importantly, do they contain the essential ingredients of life?
Comets are more or less unaltered since the birth of the solar system. They've got water in them, dust in them, maybe even complex organic molecules, the origin of the building blocks of life.
But before Rosetta can attempt to do all this, first, it has to wake up. That should happen today. It's been 8 hours. The team expected Rosetta to have made contact by now. But the radio telescopes still detect nothing but background noise.
Nobody liked this hibernation phase. We challenged it as much as possible. We were extremely reluctant to hibernate the spacecraft. But in the end, there was no other alternative.
Putting Rosetta into hibernation was a huge risk, but the team had no choice. In the run-up to Rosetta's launch, a series of fatal flaws with the Ariane space program grounded Rosetta. The catastrophe delayed Rosetta's launch by over a year. This meant Rosetta had no chance of catching its original target. The search was on for a new comet. It needed to be large enough to land on and pass close enough to the Earth for Rosetta to reach it. The scientists chose this one, Comet 67P Churyumov-Gerasimenko, a giant 2.5-mile wide pristine relic left over from the birth of the solar system. But this comet had one major downside. It was right on the limits of the distance Rosetta could travel. To reach it, Rosetta would have to go 500 million miles from the sun, further than any other solar-powered spacecraft had ever gone before. At this distance, her solar panels would no longer provide her with enough power.
Rosetta has some of the biggest solar panels ever put into space, but even those weren't big enough to operate the spacecraft safely when we were so far from the sun that the light intensity was only 4% of that which we get at the Earth.
Faced with an impossible situation, the team came up with a bold plan. To save power, they would put Rosetta into hibernation. It would mean shutting down almost all of Rosetta's electronic systems, including her gyro stabilizer, the instrument that was keeping her pointing in the right direction.
One of the main things on board the spacecraft is the system that keeps it stable, and that takes too much power. So we had to turn that off. But the problem with that immediately is that the spacecraft might start drifting away from the sun and not get any power anymore. With no power, we can't run the critical heaters, and we need heaters inside the spacecraft to keep things like the fuel lines from freezing up, because if they freeze up, we lose the mission completely.
The engineers needed to find a solution that would keep Rosetta's solar panels faced towards the sun while in hibernation.
As you can see with this spinning top here, if you start spinning something, it's stable. It stays in the same orientation all the time. So that's exactly what we decided to do with the spacecraft.
On the 8th of June 2011, the flight team gave the go-ahead to put Rosetta into a lateral spin and then shut her down. Only today will they find out if that solution worked. It's 6:15 p.m. Still no sign from Rosetta. The world's press is hungry for answers. But without contact with Rosetta, the team is in the dark.
What is the latest?
We are still receiving only noise for the time being, and any time could come the signal.
The delay could be because Rosetta's antenna is not pointing in the right direction.
After more than 2 years of hibernation, Rosetta might be pointing a funky direction. So when the spinning stops, she doesn't know where she is.
Rosetta has to work out where she is, figure out where the Earth is, then point her antenna towards it. In order to do that, she needs to open her electronic eyes.
Star Trek has little cameras which point out at the sky and take pictures of the stars and compare those stars to catalogs she holds on board. From that, she can work out where she is. Once she's locked on, she can point herself and the high-gain antenna at the Earth and send that signal which we're all waiting for to say, I'm awake.
At Mission Control, there is news. The Goldstone telescope in California has detected a faint signal at Rosetta's specific frequency. But in Australia, Canberra has detected nothing at all. Then the signal disappears. The signal returns.
It is in both stations, eh?
This time, both telescopes pick it up.
We can definitely see the signal from Rosetta. It's up there. You can see it on the screen.
After nearly 3 years in hibernation, Rosetta has come back to life.
Without today, we didn't have a mission, and now we have one of the most audacious missions ever made.
This is it. It's the beginning for us, the scientists, the operations crew. We're to get moving with the operations and do the science that we've been promising to do. It's the beginning of the venture. The beginning of the beginning, yes.
In 10 months' time, Rosetta will attempt to land Philae onto Churyumov-Gerasimenko's surface. Once there, she may be able to answer one of science's biggest mysteries. Could comets have helped seed the Earth with the ingredients of life? The countdown to the landing has begun. January the 21st, 2014. Rosetta is traveling through the outer reaches of the solar system, 5 million miles from Comet Churyumov-Gerasimenko. In the 10 years since Rosetta's launch, other space missions have transformed our understanding of comets. A NASA probe called Stardust was probably the most significant.
Oh, that's cool. Quite a trail.
Earspec has a great view.
In 2006, it returned to the Earth with a precious cargo of comet dust from the halo of a comet called Wild 2.
All stations, main chute is open. We're coming down slowly.
But when scientists examined the samples, they found that many of the dust grains had been damaged at the moment that Stardust had caught them.
Unlike the dust in my house, which is like pebbles and really hard stuff, the stardust coming off of the comet is what we call friable. It's literally like a piece of parchment that when you crumple it, it flies into a million pieces.
Dr. Claudia Alexander is Rosetta's project scientist, heading up NASA's team. In the last 8 years, NASA scientists have been able to examine a few hundred dust grains collected from the Stardust mission. And one of these grains revealed something extraordinary. It contained an amino acid, one of the essential ingredients of life.
An amino acid, glycine, was among the material that was captured. That's very exciting. This is the first time we've seen amino acids associated with comets.
Amino acids are the building blocks of proteins. They are necessary for all complex life.
The human body has maybe 20 of them, and they turn around and they produce the proteins that make our bodies what they are.
It is likely that the primordial Earth was too hot for these delicate molecules to form. So for years, scientists have wondered how these intricate molecules came about. Stardust's discovery raised the real possibility that comets may have helped seed the Earth with amino acids 3.8 billion years ago, and set off the chain of events that led to the world that we know today. If the team is able to land on the comet and drill down beneath its surface, they may discover even more of these essential ingredients of life.
We definitely want, with the Rosetta project, to find out if comets are the key.
It would add weight to the theory that comets may have helped deliver building blocks of life to Earth. But just getting Rosetta into a position where it can land Philae is a gargantuan task.
The comet is traveling about 100,000 kilometers an hour. That's 1,000 times faster than the cannonball. And you imagine trying to land on a cannonball. That's our challenge.
The safest way to land on the comet is to fly alongside it at the same speed.
Instead of letting this comet whiz past us, we have to try and ride alongside it, and then we'll deploy the lander onto the surface, and everything will be fine.
When Rosetta launched, she didn't have enough speed to travel straight towards the comet, so she had to perform a series of special speed-boosting maneuvers called gravity assists, or slingshots. The first was around the Earth.
Rosetta's flying along in her orbit around the Sun, and the Earth catches up from behind and grabs a hold of it with gravity.
The Earth's powerful gravitational force caught hold of Rosetta and hurled the craft out into space, just like a stone in a slingshot.
It flings Rosetta off at higher speed and on a new trajectory.
The Earth's slingshot accelerated Rosetta to 76,000 miles per hour. The flight engineers coordinated another 3 Rosetta slingshots, twice more around the Earth and once around Mars. Finally, in 2011, Rosetta was on target to catch up with Churyumov-Gerasimenko. The first spacecraft ever to match a Comet's speed. Rosetta is now just 1.2 million miles from Churyumov-Gerasimenko. The flight team instructs Rosetta to lock onto the comet. Message received. Rosetta's navigation cameras scan the heavens. One tiny dot stands out. Rosetta has found its target, Churyumov-Gerasimenko.
We've just seen the comet for the first time with the eyes of the spacecraft, with the navigation cameras. This is quite a moment. I mean, it's a milestone in the mission.
From this distance, Churyumov-Gerasimenko is nothing more than a blur. The scientists must take a closer look. They need to characterize the comet and spot potential hazards before Rosetta goes into orbit around it.
This is it. The main phase of the mission, everyone has great anticipation for what's coming.
Matt's team has a suite of 11 instruments with which to unlock multiple aspects of this mysterious ball of rock and ice. The flight team require this information before they can rendezvous with the comet and search for a suitable landing site.
We have no idea what this body even looks like. We have no idea what its shape is. We have no idea what its gravity is. I don't know how we're going to go into orbit without knowing those things in advance.
The scientists have just 4 months to establish Churyumov-Gerasimenko's shape, its mass, and its gravity. But the data that comes through captures something else. The comet has become active. It has transformed into a violent, erupting mass of gas, dust, and ice. This important discovery was made by Rosetta's main science camera, OSIRIS.
Okay, it's May. We've started science operations. The first thing that's come into range has been the OSIRIS science camera, and we're starting to see our first view of the comet.
The camera has detected a sphere of dust and ice around Churyumov-Gerasimenko.
It's not anymore a pinprick. It's a bit bigger than we expected, to be honest with you. It's got this visible expanse around it, this shadow, this beginning of what we call a coma, an outer atmosphere.
The coma has taken Rosetta's scientists by surprise. In the outer solar system, a comet's surface should be completely frozen. But as it moves towards the sun, it heats up, and an extraordinary transformation occurs. Geysers spew gases out of its surface, sending dust and ice into space, forming a visible halo around the comet, called a coma. The latest pictures show that this explosive activity has begun earlier than predicted. Sending Rosetta into this storm could be a huge challenge with great risk.
And we will see what has been done.
For Andrea and the flight team, this is a real cause for concern.
Now that we are approaching the comet, we have to be extremely careful. Gases coming out of the comet travel with 600, 800 meters per second, so are very fast.
Rosetta's exceptionally long solar panels act like giant sails.
Basically, the spacecraft is blown away from its position by the wind.
The comet's gas jets currently stretch 800 miles into space, but they are likely to get much bigger. Last time Comet Churyumov-Gerasimenko orbited the Sun in 2009, its coma extended hundreds of thousands of miles.
The more we wait, the closer the comet is to the Sun, the more active will be. The more gases will come out of the comet, and the more our orbit and the lander itself will be disturbed.
It will be bigger, earlier, therefore we have to try and get things done quicker.
The flight team planned to intercept the comet before its geysers grow too strong, by firing Rosetta's thrusters for over 7 hours, one of the longest continuous burns ever attempted by a spacecraft. They sent instructions to Rosetta. Rosetta confirms its rockets have ignited. The record burn pushes Rosetta into the comet's path. They will rendezvous in 3 months' time. As Rosetta nears the comet, the flight team gets some good news. Churyumov-Gerasimenko's geyser activity has reduced. The coma has died down.
To be honest with you, comets are unpredictable and we don't know exactly what's going on at the moment.
No one knows exactly why. But as the comet disperses, Rosetta's scientific camera OSIRIS is able to discern the shape of Comet Churyumov-Gerasimenko's nucleus. Churyumov-Gerasimenko looks like 2 comets that have smacked together. It's an astonishing discovery. News of the comet's bizarre shape attracts press attention from around the world. They gather at Rosetta's mission control. Today, Rosetta will rendezvous with 67P Churyumov-Gerasimenko. After traveling 4 billion miles, the flight team are about to bring Rosetta into orbit just 62 miles above the comet.
Sylvain, say the famous words, please.
We're at the comet. Yeah!
We have made history today. We're in the same orbit as the comet around the Sun, so we've rendezvous. First time ever, not bad.
Rosetta's camera now has a front row view of one of the wonders of the solar system. The comet's 2 massive heads are set 3 miles apart. Its neckline is wider than 2 Empire State Buildings standing on top of each other.
Just look at this object, it's astonishing. You've got volcanoes, you've got mountains, you've got geysers. Just the dynamic nature of this one object is really something.
We see cracks, we see what looks like fissures. These are, I think, brand new types of features for a comet. Here we have an object that clearly has potential to reveal ancient secrets. We're at the threshold of learning, which is a great place to be.
We've got boulders the size of a house. We've got these massive cliff-like structures. This is an alien landscape, and if you wanted to choose a very alien landscape, this comet has got absolutely everything that you could ever consider to be alien.
You can see this comet's quite a crazy shape. I mean, not only is it double, but if you see in the pictures we have, there's structure all over it. So it's a crazy, crazy comet to try and land on. But we've got to get down there. So the first thing we have to do is pick a landing site.
To touch down successfully, the team need to find a safe landing spot. For that, the flight team required detailed images of the comet's surface. This is what Rosetta's $100 million camera OSIRIS is designed to do. The OSIRIS team is led by Dr. Holger Sierks.
Hi, Carsten. I'm here now. So let's get going with the calibration today.
To help them operate the OSIRIS in space, they have an exact replica here on Earth, kept in a level 6 clean room at the Max Planck Institute in Germany. Despite the camera's high cost, its resolution is relatively low by today's standards.
The number of megapixels we fly on Rosetta is only 4.
10 years ago, when OSIRIS was built, a 4-megapixel camera was advanced. Nowadays, many mobile phone cameras have a higher resolution. To get the level of detail in the images that the landing team need, Rosetta flies to within 20 miles of the comet's surface. At this distance, a single mistake from the flight team could be catastrophic. Over the coming days, OSIRIS will take hundreds of detailed images in a bid to find a landing site on this jagged, boulder-ridden comet. Landing on a comet is different to landing on a planet or a moon. The comet's gravitational pull is 100,000 times less than the Earth's. It's so weak that if you jumped off the surface of the comet, you would fly into outer space. The weak gravity means Rosetta can simply drop Philae a few miles above the comet.
Philae gets pushed out of the back of Rosetta at a few centimeters a second, less than walking pace. And the very slight gravity of the comet will slowly pull Philae down onto the surface. It takes hours.
But the weak gravity presents a problem at touchdown.
So we're walking down to the surface of this comet and we land. But it's not all over then, because we'll bounce. There's so little gravity on this comet that even at walking pace, you'll bounce off the surface and we won't have succeeded. So we've got to find a way of securing ourselves to the surface.
Philae's designers spent years developing unique systems to stop Philae rebounding off the comet and flying back into space. Her 3 legs act like shock absorbers, cushioning the lander on impact. Each foot is fitted with an ice screw. The energy soaked up by the shock absorbers powers the ice screws, which will drill 4 inches into the crust. These plans were drawn up over 10 years ago. At that time, most astronomers believed that the comet's surface was hard, like ice. But a recent NASA Comet mission and data from Rosetta herself have revolutionized our understanding.
Some parts may be very ice-like. We could also have areas that are more gravelly, or even down to very dusty material. And once you consider the gravitational feel on the surface of the body itself is quite low, therefore this kind of feel that I have prodding this material here would be totally different on the comet, totally alien, in that it'll be more like prodding a kind of gravel soup or a gravel cloud more than anything, where this stuff is loosely bound by gravity.
The dusty, gravelly regions are not like anything we experience on Earth. If Philae lands in one of these regions, then its ice screws may not work. Luckily, Philae has a backup plan. 2 copper beryllium harpoons, which should secure Philae onto the surface with tough Kevlar cord. But these harpoons were also designed for ice. Landing team leader, Dr. Stefan Ulemek, wants to test the harpoons in granules of building insulation, perhaps the nearest thing to the ethereal gravel soup that can be produced in Earth's gravity.
It will be very interesting to learn if the anchor harpoon, which is designed for ice, for more solid material, would also give us some anchoring force on this very granular, very fluffy material.
The harpoons will be fired into large wooden crates filled with this material.
The worst thing that could happen is, of course, that we pull out the harpoon when we want to tension the lander to the ground. So it's interesting whether, although it's so soft, it gives enough resistivity that we can really tighten the lander to the surface, and this is part of the experiment we are doing right here.
Just like the harpoons on Philae, a 0.01 ounce explosive propellant will detonate behind the spike, pushing it out of the chamber at a speed of 201 miles per hour.
Okay, so let's do it.
Okay, let's do it.
Yep.
If the harpoons don't hold, then the likelihood of Philae securing itself onto the comet's surface will be greatly reduced. The harpoon's cord is pulled back with a force of 15 newtons. That's about the same force as it would take to pull a Venetian blind. The harpoon isn't holding. Then, dragged backwards by 4 inches, it sticks.
Yes!
We're removing now with the vacuum cleaner the dust, so we see the harpoon as it was when it actually anchored.
The reason for the harpoon's success? 4 3-inch long flukes that splayed out as the harpoon was dragged back through the loose material. Adding these simple strips of metal to the harpoon's design could save Philae's mission. But they'll only find out when they touch down. September 13th, 2014. Scientists from across the world congregate in Toulouse, France, to choose a landing site. This will not be an easy decision.
There's no smooth, flat area on that comet. There are boulder fields, there are crevasses, there are mountain ranges, cliffs. It's all there to make our life difficult.
Rosetta's team has narrowed down the choice to 5 possible landing sites. But 3 landing spots are ruled out by the team. Philae would have to pass through the comet's jets to reach landing site A, and that is too dangerous. Landing site B is littered with 329 boulders. If Philae lands on a boulder, it could tip over. If that happened, it could lose radio communication with Rosetta, and Philae's mission would effectively be over. Landing site I is rejected because it has rough terrain. They're down to the last 2. Site C is on the other side of the comet, an area called the Large Head. This landing zone may provide the best spot for most of Philae's instruments.
Over the 5 sites we had, C is by far the best.
But the flight team are concerned. Getting Philae to this location is risky, and the variable sunlight levels could cause problems for Philae's solar panels. The flight team prefers the final landing option, Site J. It's easier to reach, although it's not perfect. There are some cliffs and 93 boulders. However, some scientists continue to push for Site C.
A good site is C.
I would be very, very surprised if not J was the nominal.
No, we discussed these 2 options.
Going to C would be energetically bad because it includes a very long descent time. In addition to points like that the illumination angle is very bad.
In the end, the team agree on the safest option.
So the board has decided site J, surprise, surprise, as the nominal one, and site C as the backup.
For me, there was no one brilliant landing site. We had to choose one that was the least bad out of all of them. That's really all I can say about J.
It's risky. It may not work, but we're going to try our damnedest to make it work.
The risks may be high, but so too are the rewards. If they manage to secure Philae onto the comet's surface, then its suite of instruments can get to work. Rollis will photograph the surface. Concert will scan the comet's internal structure. SD2, a drill, will mine pristine comet material from 9 inches beneath the crust, and then deliver a sample to one of the most important instruments of all. A unique, automated laboratory hidden inside Philae's shell called Cossack. This could be a defining moment in science. The team hope that Cossack will find the special types of amino acids that are present in all living things. The so-called building blocks of life. If these special amino acids are present, it will add weight to the theory that comets helped deliver these ingredients to the Earth 3.8 billion years ago. Philae will spend months looking for them on the comet's surface. But first, Rosetta must successfully land Philae. Churyumov-Gerasimenko's jets are growing stronger, and at any moment they could erupt.
If there is a massive outburst, then we have to cope with that. If that happens, I hope it doesn't, the coma is going to start affecting the spacecraft.
Another concern is that Rosetta might not release Philae in exactly the right spot.
Rosetta's position is not that well known to within, a few hundred meters. Obviously, if we don't know exactly where Rosetta is, we can't then get the trajectory exactly right to get onto the surface.
If Philae overshoots, it could land in a boulder field. Undershoot, and it could hit these deep crevasses. Even if Philae is on target, there is still a risk that it could hit one of the boulders in the landing zone, topple over, and not be able to complete its science mission.
The major risk for the lander is really the touchdown phase. If it touches down on a cliff or on a boulder, then there's nothing we can do about it.
But if this daring mission, 300 million miles from Earth, achieves the seemingly impossible and secures its washing machine-sized lander onto the comet's surface, then this little spacecraft may answer one of mankind's biggest mysteries: how life came to exist on Earth.
We're attempting something unparalleled in spaceflight, something that not only talks about engineering and technology and risks, but has the potential for opening up whole new vistas of our understanding of where we came from.